You look up at the night sky, you see stars, you see the moon. It all seems so vast and chaotic. But it's not. Not really. The moon's orbit can be calculated. The light from those distant stars follows precise laws. The universe, from the biggest galaxy to the smallest particle, seems to run on a set of rules. And the strange part is, those rules are written in the language of mathematics. Why? Why should that be? Why isn't the universe a messy, incomprehensible jumble of stuff? Why does it obey laws that we can write down in equations? It's a deep question. It has bothered scientists and philosophers for centuries. There's no easy answer, but exploring the question tells us a lot about ourselves and our place in the cosmos. The idea that the universe is mathematical is not new. It goes way back to the ancient Greeks. Pythagoras, the guy you probably remember from a triangle theorem in school, had a whole philosophy built around it. He and his followers believed that numbers were the fundamental reality they saw in music. They found that the pleasing harmonies of a plucked string corresponded to simple whole number ratios of its length. If you have the length of a string, you get the same note an octave higher. A ratio of 3:2 gives a perfect fifth. This was a revelation. Music, this emotional, beautiful thing, was governed by simple numbers. They thought if music works this way, maybe everything does. They called it the music of the spheres. They imagined the planets moving in their orbits, creating a kind of celestial harmony, all based on mathematical ratios. Then came Plato. Plato took it a step further. He said the world we see around us is just a shadow. It's an imperfect copy of a truer, more real world. This other world was a realm of pure forms, of perfect ideas. In this realm there was a perfect circle, a perfect triangle, a perfect concept of goodness. And the language of this perfect realm was mathematics. So for Plato, when we do geometry, we're not just drawing shapes on paper. We are getting a glimpse of true reality. The universe we experience is mathematical because it's a reflection of this perfect mathematical reality. These were powerful ideas, but for a long time they were mostly philosophical. Things got really serious during the scientific revolution. Galileo was one of the first to put it bluntly. He said the book of nature is written in the language of mathematics. He didn't just say it, he used it. He rolled balls down ramps and timed them. He tracked the moons of Jupiter. And he described their motion using mathematical equations. He showed that the path of a cannonball wasn't just a random arc. It was a parabola, a precise geometric shape. Then came Isaac Newton. Newton gave us the laws of motion and the law of universal gravitation. Think about that for a second. With one simple equation, F(W)(G)(M1) M2(R2), he could describe why an apple falls from a tree and why the moon orbits the Earth. The same law applied everywhere. It was universal, and it was an equation. A clean, simple, powerful piece of math. Suddenly, the universe seemed like a giant clock. A complex mechanism, yes, but a mechanism that followed predictable, mathematical rules. If you knew the positions and velocities of all the particles in the universe, you could, in principle, calculate the entire future and the entire past. It was a stunningly successful idea. For the next 200 years, science was about finding the mathematical laws that governed everything from electricity and magnetism to the behavior of gases. And it worked. It worked unbelievably well. But the 20th century is when things got truly weird and even more mathematical. Albert Einstein came along and turned Newton's world upside down. He didn't do it by looking through a telescope. He did it by sitting at a desk with a pencil and paper. He used a type of math called tensor calculus, something most physicists at the time didn't even know. He came up with his theory of general relativity. It described gravity not as a force, but as the curvature of space-time. It was a beautiful, elegant, and deeply mathematical theory. His equations predicted that light should bend around massive objects. They predicted that time should slow down in a strong gravitational field. Nobody had seen these things. The math came first. Then, years later, astronomers looked during a solar eclipse and saw that starlight did indeed bend as it passed the sun, just as Einstein's math said it would. His equations were right. The universe was playing by his mathematical rules. And it wasn't just the very large. It was also the very small. The world of quantum mechanics was born. This is the world of atoms, electrons, and photons. And it is a bizarre world. Particles can be in multiple places at once. They can pop in and out of existence. They can be connected over vast distances in a way that seems to defy logic. It's a world that is impossible to visualize. You can't think of an electron as a tiny little ball orbiting an atom like a planet. It doesn't work that way. But you know what does work? The math. The equations of quantum mechanics are incredibly precise. They can predict the behavior of particles to an astonishing degree of accuracy. One of the most tested theories in all of science, quantum electrodynamics, makes predictions that match experiments to the equivalent of measuring the distance between New York and Los Angeles and being off by less than the width of a human hair. The quantum world is fuzzy, probabilistic, and deeply strange, but the math that describes it is exact and unforgiving. So we are back to the question, why? Why does this work? Let's look at the main ideas that people have come up with. They are all a bit mind-bending in their own way. One idea is a modern version of Plato's. It's called the mathematical universe hypothesis, most famously championed by the physicist Max Tegmark. This idea is the most radical. It says the universe isn't just described by mathematics. It is mathematics. What does that even mean? It means that reality itself is a mathematical structure. Everything you see around you, your chair, your body, your thoughts, are all part of a giant, complex mathematical object. There is no distinction between the physical world and the mathematical world. They are the same thing. Think about a computer game. The world inside the game, with its characters and landscapes, seems real to the characters in it. But from the outside, we know it's all just code. It's a set of mathematical rules and information being processed. The mathematical universe hypothesis suggests that our universe is like that. We are self-aware parts of a mathematical structure. In this view, a physicist doesn't invent an equation. They discover it. They are uncovering a piece of the universe's source code. This would explain why math is so powerful. It's not a tool we use to describe reality. It is the reality we are describing. This idea is elegant. It gets rid of the tricky question of why math and reality match up so well. They match up because they are one and the same, but it's also a very strange idea. It means that any mathematically consistent structure must exist as its own universe somewhere. A universe with different physical laws, or even one that is just a dodecahedron floating in nothingness. It's a huge, almost unbelievable vision of reality. Now let's go to the complete opposite end. This second idea says that the universe isn't mathematical at all. We are, or rather our brains are. This is the idea that mathematics is a human invention. It's a product of our brains, which evolved over millions of years to be very good at one thing, finding patterns. Our ancestors needed to understand the pattern of the seasons to know when to plant crops. They needed to recognize the patterns of a predator's tracks. They needed to understand the arc of a thrown spear. The brain that could see and understand these patterns was the brain that survived. So we have these pattern-finding machines in our skulls. We look out at the universe, and what do we see? Patterns. We give those patterns names. We call them circles, and lines, and gravity, and electromagnetism. And then we create a formal language to describe these patterns. We call that language mathematics. In this view, it's no surprise that the math we invented is good at describing the universe. We invented it for that exact purpose. It's like designing a key to fit a lock. You can't then be surprised when the key opens the lock. It was made to do that. This seems much more down to earth. It puts humans back in the center of the story. This math works because our brains are wired to make it work, but it has its own problems. It doesn't fully explain the unreasonable effectiveness of mathematics, a phrase coined by the physicist Eugene Wigner. Why should mathematical concepts, invented for one purpose, turn out to be perfect for describing something completely different, something nobody had even thought of yet? Yes. For example, a couple of thousand years ago, the Greeks studied conic sections, the shapes you get by slicing a cone circles, ellipses, parabolas, and hyperbolas. They did it for fun. It was pure abstract geometry. There was no practical application. Then, centuries later, Johannes Kepler was trying to figure out the orbits of the planets. He discovered they moved in ellipses. The math was already there waiting for him. Why? Even more strange are imaginary numbers. The square root of -1. It's a concept that seems completely absurd. It was invented by mathematicians as a kind of mathematical trick to solve certain equations. It was a curiosity. Then, in the 20th century, when physicists were developing quantum mechanics, they found that imaginary numbers were essential. You cannot describe the quantum world without them. So how did a mathematical game, a figment of the imagination, turn out to be a fundamental part of reality? The human invention idea struggles to explain this. It seems like too much of a coincidence. This leads us to a third possibility. This one is a bit more subtle. It's related to something called the anthropic principle. The basic idea goes like this. Maybe there are many universes. Maybe there's a multiverse. And maybe each of these universes has different laws. Some are chaotic messes, some are empty, some last only for a fraction of a second. In most of these universes, there are no stable structures. No stars, no planets, and certainly no life. But in a very small fraction of them, the laws happen to be just right. They are stable, ordered, and consistent. They are the kind of universes where complex things like galaxies and life can form. And what does it mean for a universe to be ordered and consistent? It means it follows rules. It means it has a kind of logic, a kind of structure that can be described. It means it's a universe that would look to any intelligent creatures that evolved within it, mathematical. So, the reason we find ourselves in a universe that is so mathematically perfect is because we couldn't exist in one that wasn't. It's a selection effect. It's like asking why Earth is so perfectly suited for life. We have liquid water, a stable star, a protective atmosphere. Is it a miracle? Not if there are trillions of planets out there. By sheer chance, some of them are going to be in the Goldilocks zone. And of course, that's where we find ourselves because we couldn't have evolved on a gas giant or a frozen rock. We are here asking this question because we live in one of the rare universes where the conditions were right for us to be here. And one of those conditions is that the universe is orderly enough for us to exist and to understand it. That order is what we call mathematics. This idea is appealing because it doesn't require reality to be math, nor does it rely on human invention. But it's also deeply unsatisfying to some because it's very hard to test. We can't see these other universes. It might just be an untestable story. There's a fourth option too, and it might be the most honest one. Maybe the universe isn't so mathematically perfect after all. We tend to focus on our successes. Newton's laws were a triumph. Einstein's equations were a masterpiece. The standard model of particle physics is astonishingly accurate. But we also have huge gaps in our understanding. For one, our two best theories of the universe, general relativity and quantum mechanics, don't work together. General relativity describes the world of the very large, of stars and galaxies. Quantum mechanics describes the world of the very small, of atoms and particles. Both are incredibly successful in their own domains. But when you try to use them together, like to describe what happens inside a black hole, or at the moment of the Big Bang, the equations break down. They give nonsensical, infinite answers. We have been trying to unite them for decades with theories like string theory, but we haven't succeeded yet. So our mathematical picture of the universe is not complete. It's broken. And then there's the stuff we don't understand at all. We look out at galaxies and we see that they are spinning too fast. The gravity of the stars and gas we can see isn't enough to hold them together. They should fly apart. So we invented a placeholder called dark matter. We think it's some kind of invisible particle that provides the extra gravity. We can describe its effects mathematically, but we have no idea what it is. It makes up about 27% of the universe. Then we see that the expansion of the universe is accelerating. It should be slowing down due to gravity. So we invented another placeholder called dark energy. It's some kind of mysterious force pushing everything apart. It makes up about 68% of the universe. So the stuff we understand, the matter and energy described so beautifully by our equations, makes up less than 5% of the universe. The other 95% is a complete mystery. We just give it a name and a mathematical placeholder in our models. Is that a mathematically perfect universe, or is it a universe that we are only just beginning to understand? Perhaps our current mathematics is just a very good approximation for the small part of the universe we can see. Maybe the ultimate reality is much messier, much more complex, and maybe it isn't describable by the kind of elegant mathematics we've come to love. So where does this leave us? We have these competing ideas. Is the universe a mathematical structure? Is math a human invention to describe patterns? Are we just lucky to live in a universe that happens to be orderly? Or is our idea of a perfect mathematical universe just an illusion based on our limited knowledge? Nobody knows for sure. It's possible the real answer is a mix of all these things. Maybe the universe does have a fundamental logical structure, a kind of pre-mathematics. And maybe our human brains evolved to be able to tap into that structure, to invent a language, our mathematics, that aligns with it. And maybe we are a product of the Anthropic principle, an island of understanding in a multiverse of chaos. What's so compelling about the question is how it makes you think about the relationship between our minds and the world outside. When you see a beautiful equation that describes the real world, like EMXE2, what are you really seeing? Are you seeing a piece of the universe's code, as Tegmark would say? Are you seeing a brilliant summary of patterns, a triumph of the human mind? Are you seeing a clue about the nature of reality itself? Maybe the word perfect is the problem. It implies a finished, complete system. Science isn't like that. It's a process of refinement. And Newton's math was perfect for its time, but it turned out to be an approximation of Einstein's deeper reality. And it's very likely that Einstein's reality is just an approximation of something even deeper. We keep peeling back layers of the onion. With each layer, we find that the world is more subtle, more strange, and more beautiful than we thought. And at each layer, we have so far found mathematics waiting for us. Perhaps the most amazing thing is not that the universe is mathematical, but that we can understand it. We are a collection of atoms forged in the hearts of stars. We live for a short time on a small planet in a vast cosmos. And yet we can look out of that cosmos and write down equations that describe its past, present, and future. We can use those equations to build technology, to send probes to other planets, to understand the beginning of time itself. Eugene Wigner called this the miracle of the appropriateness of the language of mathematics for the formulation of the laws of physics. He called it a wonderful gift which we neither understand nor deserve. Maybe he was right. Maybe we shouldn't ask why the universe is so mathematically perfect. Maybe we should just be grateful that it is, and that we, for some reason, have the ability to appreciate it. The search for an answer continues. Physicists are smashing particles together in giant colliders, looking for new physics that goes beyond our current equations. Mathematicians are exploring new, abstract structures with no thought of practical application that might one day be the key to the next revolution in physics. And we all can look up at the sky and wonder. The mystery itself is part of what makes it so profound. The fact that we can even ask the question is, in its own way, an answer. It tells us that we are not separate from the universe. We are a part of it. We are the universe trying to understand itself. And the language it seems to be speaking is math.